Hi class, so today I'm going to be discussing resonance and differences in octet variances, meaning compounds or atoms that do not meet the octet rule and others that exceed the octet rule. And some of these are going to be important for next chapter because we're going to start studying their shapes. Okay, so Lewis structures. This is not to do with really resonance or octets, but it's something I wanted to cover in a couple slides. You will start dealing with compounds that have more than one center atom, meaning here's the nitrogen. In this case, you have an N and you have an oxygen. So I want to go over how to give you hints on how to put these together. So in this case, you see the N has two H's with it, and then it has an oxygen and an H. This is how you put the compound together. So you put the N and the H's are together. That's why you don't have NH3 in an oxygen. It's basically giving you how the compound should be put together. So in this case, N is the center atom, and then you have two H's joined to it, and then you actually also have an oxygen joined. And this H that's attached to the oxygen, and it shows here, this is an alcohol. So this H goes with this oxygen. It does not go on the nitrogen. So this is things that I'm not sure the book has really pointed out, so I want to help you guys so you're not struggling with this. Here's another one. We have ethanol. Now, ethanol can either be listed as this, which you have no idea how to put this together, or it could be listed as this. And if it's listed as this is telling you exactly how the compound is. You have a carbon with 3 hydrogens. You have another carbon with 2 hydrogens. And then you have, here's that OH again. And you have another OH, and that H is attached to that oxygen. So this is telling you exactly how this compound is. And if you notice, so you have 1, 2, 3, and you have a fourth bond. You have 1, 2, 3, and you have a fourth bond. Oxygen, if it's got 2 bonds, it will always have 2 lone pairs with it attached. And then an H. And it can be this way, and it's very stable. Same thing as here. Nitrogen can always have a lone pair. So if you look at this, if you cover this H up, then you actually see that this has 3 bonds and a lone pair. So these are little ways to help you understand if you start looking at more complex molecules, compounds, how to put them together. If you're given it this way, then it means it's testing you to create the structures and determine which one is the most stable, is probably what's going to ask, or wants to see how many structures you can put out there. If you have to create the structures, you can change these all around. You can have a COC and just kind of mess with this, because this one doesn't have any rules. It's not telling you where the hydrogens or the oxygen is bonded. And then you would have to use formal charges to determine which one's probably the most stable. In this case, I'm not asking you to do that. So I hope that helps. One more thing, if you're looking at center atoms, and this does it, you always want the least electronegative. So here is carbon. Carbon is a center for this part, and it is more it's lower electron, it's smaller value of electronegativity than oxygen. Same as carbon here. And nitrogen is lower electronegativity than oxygen. The more electronegativity atoms tend to be in the ends. The ends, bookends is what I call them. Like dead end streets. These are how I used to visualize them as a student, because they pull the electron density away from the compound. So it's easier to do that if they're on the end than if they're in the center. So I hope this helps you understanding, because you're going to start looking at more and more complex. And I have run into students that don't know this, and for some reason the book's not pointing it out. And in actuality, I didn't learn most of this until I got into organic chemistry. So I just wanted to help you guys a little bit with that. Okay, so resonance is what we're going to cover now. Resonance is not an easy thing to learn. It's hard, and you always feel like you're doing it wrong, but just keep going with whatever it is that you're doing. That's the best I can tell you. Same rules for chemistry. Well, Lewis structures help visualize a bonding. So I'm going to read this, and then I'm going to give you examples, because it's the best way for me to explain it. Lewis structures help visualize bonding. There's some limitations. So when you do the Lewis structures, what you're going to find is you've got these weird things going on where some of the atoms, they don't fit into the rules of the octet. In fact, they break all the rules that you've just learned. So we've told you something, and now we're going to take it back and say, just kidding, there are some exceptions to that. It is what it is. We all learned it this way. So one Lewis structure is not going to work with some compounds. It's just not going to work. You're only getting a representative of one structure, and you're going to have to actually draw more structures to show that what this resonance is. So what is resonance? Resonance is, let's jump to this bottom here. So you have localized electrons. They are specifically on one atom or shared between two bonds. So when you see a bond, let's go back one. When you see a bond, these electrons are localized. They are strictly between this nitrogen and this hydrogen. When they're delocalized, they are shared between multiple atoms. This is why you need multiple structures to show that it's not just on one bond, it's on multiple bonds. And you have to move these electrons around to show them on different bonds. So when you have compounds or ions that have more than one structure, they're called resonance structures. Now, the key thing that you have to remember when you do these is that the structures themselves do not change. It's only the electrons that are moving. The placement of multiple bonds and lone pairs, but the structures themselves, the skeleton structures that you draw with a Lewis structure, does not move. Hold on a second. Okay, sorry, my son. So there's one thing too you can kind of look at. You can look for specific things to determine what resonance structures are. So this looks like a little different color here. Resonance structures are particularly common in exoanions. That means oxygen. Oxygen is a part of another anion, and those structures usually can hold more, exceed the octet. They can do other things, and it's, let me show you here. They're not always easy to explain. Okay, so we have carbonate ion. It has a charge, but within itself, these are all nonmetals that share. So you can see there are three structures here, and what you notice here is that the bond, there's a double bond here, but then it moves to here. No, it moves down here on this one, and then it moves up here. Totally not clockwise. And it's a double arrow. Now what you need to understand about this, so this is delocalized. This electron pair is shared between all three of the carbon-oxygen bonds. And when they've done studies, they've found this. It's not a double bond. It's not a single bond. There's some existence in between, but you can't show that. The double-ended arrow does not mean there's three structures. What this means is you have to kind of visualize that there's electron sharing between all three of these that is going on. But do you notice the structure itself has not changed? It's just a bond and a lone pair. That's it. So if you create a structure, keep the structure exactly how it is, but you have to move it, and you have to keep remember when it's got a charge, when you're dealing with anions, polyatomic ions, you have to put a bracket and you have to put the charge, always. If you were to ever give this to me, if we were in class and I had you draw these out and you didn't put brackets and charge, I would mark this completely wrong, because you're now showing me just a non-metal sharing themselves, sharing electrons, but not showing that this is actually an ion. Okay, but we're not, so you don't have to worry about that. Excuse me. So what you need to see, hopefully I'm making sense with this, is one molecule, the double arrows there to help you create a mental picture of the molecule by fusing the various resonance structures, not going back and forth between them. How would you know that you would have to do that? Well, you wouldn't. But there are some key things, and there's the hardest thing about this, that there's no rules. There's no rules to tell you. I mean, there's little rules, but there's no tips to tell you how many structures you have. There's no tips to tell you that you're actually dealing with the resonance structure. You have to just have the knowledge, which is what I'm giving you now, to be able to figure this out. So let's say you drew this compound, okay? There are certain things that are indicating that this is a resonance structure. It's very symmetrical. It's got oxygen on it, and it's got a double bond, but yet it's got two oxygens that have single pairs, lone pairs on it in a single bond. That means that this double bond can move, and you can have another structure that has a double bond here, and then you can have another structure with a double bond here. These is not easy to learn at first, but that's what some of the things that I'm giving you. It's oxygens all around it, and it's symmetrical. Every outer atom is the same with one double bond. That's usually an indicator that this is a resonance structure. Now, it's not black and white like that. It's easy for other things, but these are good tips. If you see some of that stuff, you might want to try moving some of these bonds around to see if there's another structure to it. Okay? What it really looks like is like this. This is a hybrid. It shows you that the electron density of the pair is spread out between all of them. I'll be honest with you. I don't know why they just don't teach it to draw it like this, but they don't. And I don't create the rules. So if you were to ever have to give me something, you would have to give me those three and not that. But that's how it looks. Now what I did is I found a benzene with a GIF. So you can see how the bonds are moving. I couldn't find one that matched this. Nobody made one. So if you guys know how to make GIFs, make me one of these, please. This is how the bonds are moving. So they're constantly showing that this electron pair is it's delocalized on all these carbon to carbon bonds. These are carbons. If you guys don't know how to draw this yet, these are carbons. Every line here that are attached are carbons. This is benzene. It's a toxic chemical. It was actually found in drinking water, I think in the 80s in Long Beach, I think, and other places. Very bad stuff. I worked with it when I was one of my internships at Caltech. Excuse me. But this is the compound itself. And so it's delocalized around all of these. So it's not going back and forth. The compound is not going back and forth like this. It's one compound that actually looks like this. So if you drew this would have the dashed lines between all of these, that this electron pair is delocalized on all of them. Okay, here's another one that has delocalized. Oxygens, one's a double bond, the others are a single bond. In this case, there's only one. This is a good indicator that this has got a resonance structure to it. It's very symmetrical. If they're symmetrical, most likely they've got some resonance structures, and you're just gonna have to figure out usually how many oxygens on it. Usually, not always set in stone, is how many resonance structures there are. So if you see here, there was 3. We have 3 structures. This one has two structures. Okay. Another thing to learn is if you have an oxygen that has a single bond, it has 6 electrons around it. If you have double bonded oxygen, it has lone pairs, 2. That's usually how this goes on every compound. You'll see either this or see that when it comes to oxygen. Very rarely will you see something different. The only other one you'll see is if we go back, you'll see that this has 2 bonds, but 2 lone pairs. So in a sense, this double bond is now a lone pair on that other one. But you can see, I labeled it as 2 bonds, not just necessarily a double bond, but 2 bonds, even though I listed it here as a double bond. So a double bond with 2 lone pairs, or it could be 2 bonds connected to an oxygen with a lone pair. As you start drawing more molecules, you'll see a trend to all of these. So here's another delocalized resonance structure that it's being shared between all of these on here. Okay, so now let's get to exceptions to the octet rule. There are 3 types of ions or molecules that do not follow the octet rule. There are odd number of electrons. There are ones with less than an octet, and then we have more than an octet. And the last 2 on here are ones that are going to have more of an impact in next chapter when we start having to deal with geometry and shapes and so forth on this, which some of our lab this week will have to do with that. So, and let's cover the odd number of electrons. These are radicals. They are very unstable. They will react as fast as they can. Because they are so unstable, they want to attach themselves to something because of how reactive they are. That's pretty much all you need to know about. I'm not going to cover more about that. Know that they are radicals. They're odd number of electrons. Keyword being odd number, very reactive, very unstable. That's about it. Okay, fewer than 8. So we have elements in the second period before carbon that can make stable compounds with fewer than 8 electrons. And it's usually aluminum, boron, or barium. They are very stable, not fitting the octet rule. So consider we have boron with 3 fluorines attached to it. So as you can see, this is actually 6 electrons. And if you did the formal charge, you would actually notice that some of these are not as actually, it doesn't tell me if it's formal charge, but it doesn't matter. It's telling you that this is the dominant form on here. And, oh yeah, this is why. If you actually put a double bond to fill an octet and you do the formal charges, what you find is that boron will have a negative charge. You do not want boron to have a negative charge. Boron's not supposed to be more electronegative than fluorine. Fluorine is the most electronegative atom on the periodic table. So these are not stable. So it would be this one, which means that it would have 6 electrons and not the 8 that are filled here. So if you haven't covered the formal charge video, I strongly suggest you do, because everything, all of this is related to formal charge on here. Okay, another one is beryllium. It's group 2, but it has 4 electrons. So it has 2 and then it shares 2, and it is very happy like that. Now some of these can attach to other compounds, but I'm not getting into the more intricate stuff. So we're just learning right now of atoms that have less than 8 electrons. And beryllium and boron and aluminum, very happy with not having it. Aluminum has 3 valence electrons, which means it can take 3 more electrons, and that gives it 6, and it's happy like that. All right, so exceeding an octet. This is the part that has people have a hard time with, because it breaks the rules a little bit more. Less than octets kind of makes sense to people. Okay, that's fine. But when they exceed, it's harder to understand. If it's n equals 3 and on, you have 3d orbitals, you have 4d orbitals, you have all more orbitals that are not used, but we can use them and attach and exceed the octet. Now here's a rule, a tip. And I have it bold, expanded valence shells occur most often when the central atom is bonded to a small electronegative atom such as fluorine, chlorine, or oxygen. When you're dealing with these and things aren't making sense, keep going, because most likely you are exceeding the octet and it's going to work. It's meant to work. There are compounds that do not follow the octet rule depending on what it's been given. So size is also important on here. Okay, so let me jump back. Third period elements occasionally exceed. Sorry if I've been talking fast. I've been sick with the flu from my 2nd vaccination. So now I'm finally able to talk. I haven't been able to talk. Elements occasionally exceed the octet rule by using their empty d orbitals. Size is also important consideration. The larger the central atom, the larger number of electrons which can surround it. So look at the trend when it comes to atoms and increasing size, and how they go up or down a periodic table. That's very important, because that can help you understand that if it's larger, it can take on more electrons. So here is some examples for you. When an element is in a period 3 or below, it can use the d orbitals. So we have phosphorus and we have 5 fluorines around it. Normally, if you tried to draw this and didn't know this rule, you would say no way. But phosphorus is n equals 3 or below, and it absolutely can have this. And you see this fancy molecule? This is what we're going to be studying next chapter. So phosphate will actually have 4 resonance structures with 5 bonds on the phosphorus atom. So you can see this is when the formal charges start coming in, so you can start picking out which one's probably the most stable, but you would also have to understand that there's more to them going on. All right, so here's some more examples so you can see even xenon. So we lied to you, and I was lied to the same way. Noble gases can actually form bonds with compounds, but we don't cover that until right now. And in this is all we're going to talk about it. We're never going to talk about why, where, what. That goes into more deeper chemistry, which you guys don't want to know right now. So xenon, so noble gases can, depending on where they are, can form bonds and can form more bonds. It can form more bonds than this. But this is an example to give you. If they're n equals 3 and you're given a weird compound, just go with it, because chances are it's going to be exceeding an octet, but it will still work. And why am I bringing these up? Because next chapter, we're going to start looking at these and determining what they look like with this. So I want to give you guys an idea, make yourselves a little familiar before we tackle this. And I'm going to show you guys, I have a video showing you how to create Lewis structures. It works with n equals 2 and up, meaning n equals 1, very well. But there's a lot of atoms there that can be made from it, even with more than one center atom. What it doesn't do well is if you plug in my little, what I show you, kind of my cheat sheet to show you how to do this, if it's n equals 3 and below. It can give you a guide, but then after that, you'll have to actually test the formal charges and try to move bonds around. But you can still use it. You just need to understand that what you're getting may not actually be the most accurate or more stable. I found this online, and this is another way that you can move things around. This is more to show you how somebody put this on their site of how to create this. So this is a Lewis structure of perchlorate ion. And this is the steps that they did, which are different than mine, but any ways that you can learn how to do things. If my way doesn't work for you, maybe this way will. So you follow the steps that are required. You find the total number of electrons, of valence electrons between the chlorine and the oxygen atoms, and including the charge. The charge is very important. If you don't count the charge, this will never work. Determine the center atom from chlorine and oxygen. Chlorine is lower in electronegativity than oxygen, so it's going to be the center. But here's another tip. Even if you didn't know that, usually the atom that's by itself is the center, because you want things to be symmetrical. Symmetrical usually is the lowest in energy. So even without knowing that, you probably would try it with chlorine in the middle, because the rest of them, it would be very off without that. Okay, so once you determine the valence electrons, just put the lone pairs on, and then you determine the stability by doing the formal charges. So I'm going to break this down step by step. Okay, so first things, we need to know how many. We have 1 chlorine, 4 oxygen atoms, and there's a -1 overall charge. And you have to count that. If you do not, or if you're dealing with something like NH4+, if you don't take that electron away, you will never get the compound right. These ion charges make and break these compounds if you're trying to put them out as Lewis structures and so forth. So chlorine has 7 electrons and oxygen has 6. So for chlorine we have 7 times 1 = 7. For oxygen we have 3, and we have 3. Why does it say 4? Wait a minute. No, we have 4. Sorry about that. There are 4. This should be a 4 here, not a 3. That messed me up for a second. 6 times 4 = 24. So we add those all together, but we have to add the negative charge that's on it, which is right here. So you add that 1 electron as well. So this is 32 electrons. Okay, so the first thing you do is you draw a skeleton. This is a skeleton structure. So we know that this is 2, 4, 6, 8. We've already used 8 electrons on this. And then we just start filling them in. And we do leave them as single bonds. So leave them as single bonds. And now you have, excuse me, you have 1 oxygen that takes 3 lone pairs, fills the octet. And you notice that there are no lone pairs left on chlorine. So everything's been taken care of. They've all filled in. But is this the most stable structure? We don't know. The next thing it says is to check the formal structure, the formal charges, which is now what you're doing. So when you find this, you notice that this is a +3 and there's 3 negative charges. This is very high number for chlorine. This is not stable at all. We need to get this. The rule is the best formal structure is the one that has either a 0 charge overall or a charge that matches the compound. This does not match the compound. This is too high. For the least electronegative atom, this oxidation state is way too high. And we don't usually want formal charges on every atom. This is also not really working. So we are going to move one of those pairs and create a bond. So what you do is you visually, and if you go into organic, if any of you, this is all you're going to do. You will move this over and create a bond. Now you're going to check the charges. This ends up being 0, and then you have a negative, -1, -1, and a +2. Still too high and still too many charges on the single bonded oxygens. So this also still doesn't work. So we're going to do another one. So you're going to move this one, and you're going to keep it symmetrical, because everything in chemistry is keeping things symmetrical. They're most stable. So you don't want to do one just right here. You want to do it symmetrically as you draw it. So you're going to move that down. And now as you move that down, it moves this to a plus charge. And now you have a -2 charge. Most would think this is good. Technically, it is acceptable to a point because it has filled everything. But having 2 charges on 2 atoms and a plus charge really doesn't work. You still want, if you can go down further, you absolutely should, because it's not as stable as it could or should be. So you're going to do it again. So you're going to do one more, and you did one more. Now you have a 0 charge. There should be a 0 charge on here, and this is a negative. And this is the most stable because you are actually dealing with only 1 charge that matches the compound, and everything else is a 0. So this should work. This is the most stable compound. This is how you do Lewis structures. You have a lot of drawing. You make a lot of mistakes. Find a pencil and an eraser, because when you do a lot of this stuff, you will be erasing a lot. But this is a step-by-step to show how somebody figured out which is the best structure for this. Okay? So this is an overview on that same page I found where they just kind of put things together. You can look at this if you want, but this explains a little bit more. Okay, so this is my overview of everything I've talked about to give you information. There's no quick formula to determine if a structure is a resonance structure and how many exist. You kind of have to look for compounds that are symmetrical, which I have listed here. Oxygens tend to be what is around a resonance structure. And the amount of oxygens, based on what my perception is, the number of oxygens tends to tell you how many resonance structures you're going to have. Usually involves a double bond, and then the rest single. That's another key. Expanded valence shells occur most often when the central atom is bonded to small electronegative atoms such as fluorine, chlorine, or oxygen. Sorry, excuse me, I had a pause. I had a cough. I'm still not completely better. If you exceed an octet, make sure that the atom is n equals 3 or below in the periodic table. Resonance structures. Electrons move, but the structure does not change. You do not move the skeleton structure. You don't move or break or form a new bond, so you don't add to it. The only thing you do is you move an electron pair, and when you move the electron pair, then that either adds a bond or you remove a bond, but you represent the electron pair for that one bond. Check formal charges for all atoms to determine most stable, and there's some tips with this. Lowest charge or zero charge is usually the most stable. I meant to remove that. If there is a charge, it should be on the most electronegative atom, which it was for the one I showed you. It was on oxygen. Some atoms that can have an octet, xenon, sulfur, phosphorus, chloride, iodine, and bromide. Remember, as you go down a periodic table, they get bigger. So that is showing you how some of these can get bigger and bigger, and they can have a greater, they exceed the octet. Okay? And that's it. Thank you.